Okay, welcome to part 2 of cardiovascular physiology on the heart. So our bodies are good conductors of our electricity. Cardiac depolarization and repolarization occur in waves through the heart tissue during each heartbeat. This causes electrical current to flow from the areas that are depolarized to the polarized areas. And this occurs in large circuitous routes. You can see here in this diagram, this guy is mid-heartbeat. You have a wave of depolarization traveling down the ventricular septum, and this will spread to the walls of the ventricles and then cause the whole ventricles to contract during the ventricular systole. You can see at this snap point, the ventricular septum is negative, whereas the walls of the ventricles are positive. So this causes current to flow between the positive and the negative areas. Now this current flow can be detected by placing electrodes on the skin near the heart, or even on the arms and the legs. And this detection is called the electrocardiogram. This is when you detect the electrical current moving around the heart during the heartbeat. This records electrical events within the heart. So you can see different parts of the heart have different shaped action potentials, and when you summate all of these action potentials throughout the whole heart during a single cardiac cycle, you get the ECG trace, which some of you may recognize. So a voltmeter records this electrical potential across the heart using electrodes placed at different areas around the body. The output is a graph. You have x-axis, which is time, obviously, and the y-axis is the amplitude of the electrical signal that's being measured. And this amplitude is proportional to the number and size of the cells that have have the electrical activity. So this is the most common ECG limb lead arrangement. It's called the standard bipolar arrangement, and there's 3 types. There's arrangement I, or III, which is obviously Roman numerals for 1, 2, and 3. Bipolar meaning the electrical potential is recorded from 2 electrodes located on different sides of the heart. So the first arrangement, you can see the positive electrode is on the left arm, negative electrode is on the right arm, whereas the left leg is the ground electrode, and it's measuring electrical activity from the right to the left direction. So you can see the direction of this red arrow. Whereas limb arrangement 2, you have the positive electrode on the left leg, the negative electrode is on the right arm, and the left arm is the ground, and then you can measure the electrical potential in this orientation from the right arm to the left leg. And finally, limb arrangement 3 for the bipolar leads is negative electrode on the left arm, positive electrode again on the left leg, and you're measuring the electrical activity in this direction down diagonally to the left. And these 3 limb lead arrangements give slightly different ECGs, but they're more or less the same, but you get different magnitudes. So there are 3 major components of an ECG trace. We have waves, which are part of the trace that go above or below the baseline. For example, P, Q, R, S, T, and U are the most common. We have segments, which are sections of baseline between 2 waves. For example, we have this PR segment here, which is from the end of the P wave to the start of the R wave. You may think that we should include the Q wave. The Q wave can be very difficult to see on the trace, so usually we call this the baseline between the end of the P and the R wave. And then finally intervals, which are combinations of waves and segments, such as this PR interval here, which is from the start of the P wave to the beginning of the R wave. So let's go through the ECG trace and match it to what's occurring in the heart during a single cardiac cycle. So we can see here at the start, we're beginning to have the atria starting to depolarize. So the signal is being sent from the SA node and is starting to move through the atria, causing the atria to start to depolarize. And this coincides with the P wave. Once the atria are completely depolarized, the ECG trace has returned back to baseline. So we only see a deflection in the ECG trace when parts of the heart are in the process of either depolarizing or repolarizing. If the whole part of the heart is either depolarized or repolarized, it is baseline. It's only when it's sort of halfway through doing one or the other when we see this deflection. So once the atria are completely depolarized, and when this will cause them obviously to contract, we're at this region here in the ECG trace. So the ECG trace is at the baseline. And then when the electrical signal has gone through the AV node and is now transversing the interventricular septum, causing only the interventricular septum to depolarize, this is the rest of the ventricles to remain repolarized. We see the Q wave. Then when the signal starts to spread out, the depolarization starts to spread out through the ventricular walls, we see the large spike in the R wave. And then when the ventricles are just about completely depolarized, we see the S wave. And once the ventricles are completely depolarized, we return back to baseline. And once the ventricles obviously are completely depolarized, this will be when the ventricles will be contracting. And you can see that it's labeled on the diagram, this red line, ventricles contract. And when the ventricles start to repolarize, this is what is shown as the T wave on the ECG trace. And then once the ventricles have completely repolarized, and the atria are not starting to depolarize, so the whole heart is basically at resting membrane, you get this flat portion of the ECG trace, so the baseline. For the heart is resting, then it's the baseline on the ECG. And then it obviously goes back in the circle during the next cardiac cycle. So the SA node will then initiate a new action potential to start a new heartbeat. Atria start to depolarize, you see the P wave again. So this is showing you the same thing, but in this case in a straight line. And you can see how it also shows you the different systole and diastole within the heart. So atrial systole occurs after the P wave has occurred. So this is an important point you need to make sure you understand. The electrical activity always precedes the mechanical response. So this electrical signal occurs first, and then you have the mechanical contraction of the muscle. So the electrical activity of atrial depolarization is the P wave. So you'd see that on the ECG trace first, and then the atria will contract, pushing blood into the ventricles. Similarly, you'll start to see the QRS complex, which is the ventricle depolarization, occur first, and then the ventricles contract, causing blood to be ejected into the arteries. Then once the ventricles start to repolarize back to normal, you get the T wave. So once again, this is the ECG trace with the different segments, waves, and intervals labeled. Now obviously, it's not important that you memorize this whole thing. So obviously you need to know the different waves. P, Q, R, S, T are the main ones. And let's look at some important intervals and segments. So the PR interval, shown here, the start of the P wave, the end of the start of the R wave. So this is beginning the electrical excitation of the atria to the beginning of the excitation of the ventricles. So if this interval is delayed or extended, it could indicate a delay in the signal conduction through the AV node. The QT interval is the time required for the ventricles to undergo a single cycle of depolarization and repolarization. You can see here it's from the Q, beginning of the Q wave to the end of the T wave. Long QT syndrome can cause development of arrhythmias. So if this interval is extended, it can lead to cardiac arrhythmias. Finally, the ST segment, shown here, from the end of the S wave to the beginning of the T wave, is when the entire ventricular myocardium is depolarized and the cardiomyocytes are in their plateau phase, if you remember from the last lecture. And that elevation here is often seen following myocardial injury, and it's called the current of injury. So this is when this interval is not actually baseline, and it's actually elevated. And then the RR interval is basically the largest wave, so the R wave is basically the largest wave, so this interval is the easiest interval to use to calculate heart rate. So you can see these R waves, the easiest on ECG trace, so these waves are used most commonly to calculate heart rate, by just measuring the time in between each of these peaks, and you can measure heart rate from that. So to calculate heart rate, it's very easily, as I mentioned, it's commonly calculated from RR interval. So if you know the time interval between each R peak or R wave, then you divide that into 60, then you can calculate heart rate very easily. Now let's look at a few other things related to heart function. First of all, let's talk about preload. So during diastole is when the heart is relaxed, and this is when the heart is filling with blood. Hopefully you can remember that from the last lecture. Now preload is the degree of stretch on the ventricular wall by the blood filling the ventricle. So as blood fills and rushes into the ventricles, it obviously causes the ventricles to expand, because the ventricles are somewhat elastic to allow them to fill with blood. And if you fill these ventricles with blood, it puts a load on these ventricles, and this load is called the preload. So the degree of stretching of the ventricle is called the preload. And it's obviously more filling means higher preload, which means the ventricles have to expend more energy to eject blood into the arteries. So this is obviously proportional to end diastolic volume. And remember, end diastolic volume is the amount of blood in the ventricles before they beat to eject blood into the arteries. And that depends on the venous return to the heart. If you increase the venous return to the heart, you increase the filling of the ventricle, which increases end diastolic volume, which causes an increase in preload. So the heart would have to work harder to eject this larger volume of blood. This preload controls stroke volume. If you increase preload, you're going to be increasing stroke volume. It's obviously because you increase the amount of blood in the ventricles, which increases preload, which causes an increase in stroke volume. And remember, stroke volume is the amount of blood being pumped by the heart per heartbeat. Now, why do you think it's important that if you increase preload, you increase stroke volume? Now, if you have a think about it, it should be fairly logical. If you increase the amount of blood being returned to the heart, if you don't have some mechanism by which you're also increasing the amount of blood being pumped by the heart, then this blood is going to start backing up if it's not all being pumped by the heart. So increasing venous return, you need to have some mechanism to increase the stroke volume, otherwise blood will start to block up the heart or start backing up. This occurs during heart failure when the heart can no longer beat all the blood that gets returned to it. Obviously, when we're healthy, we need the heart to be able to pump all the blood that's getting returned to it. So the relationship between preload and stroke volume is called the Frank-Starling law of the heart. This is where when stroke volume is increased in response to an increase in end diastolic volume by increasing the preload. So you can see here it's graphed on this figure down here. Along the x-axis we have the end diastolic volume, and obviously when we're increasing end diastolic volume, we're increasing the blood in the ventricles, which is increasing the preload on the ventricles. And on the y-axis we have the force and the stroke volume. So obviously stroke volume increases due to increased force. So you can see at this normal resting value, we have 135 milliliters in diastolic volume, which equates to about 70 milliliters stroke volume. Then when we increase the filling of the heart, we're increasing the stroke volume and the force being generated to result in the stroke volume. Now obviously the heart cannot keep doing this indefinitely. There comes a point where you fill it to such an extent the heart can no longer increase stroke volume or the force to increase the stroke volume. You start to plateau and maybe even start to decrease at the end. But during normal physiological levels, you see a linear relationship between filling of the heart and the power generated by the heart to pump this blood. And why is this the case? Well, if you need to go and look at the heart itself, the cardiomyocytes, and look at the striated muscles. Hopefully you can remember this from your skeletal muscle lectures. The cardiac myocytes are very similar to skeletal muscle in that they're striated. They have actin, myosin, and to contract these cells, you need this actin and myosin to move against each other, and they move together to cause contraction. And different stretching of these actin myosin causes different amounts of overlap. So you can see here, resting sarcomere length is along the x-axis, and then the tension developed is along the y-axis. So increased filling of the ventricles will cause increased stretching of these filaments against each other, allowing there more space to contract, generating more force. But if you overstretch them, and then this is when you start to see this force dropping off. But under normal physiological distances or normal physiological loading of the ventricles, we lie mainly within this part of the graph. So when we get increased stretching by increased blood filling the ventricles, we're getting better overlap of the actin myosin, which allows us to generate better tension and force of contraction, allowing us to increase stroke volume. So this is exactly the same as what occurs in skeletal muscle. It's the length-tension relationship, where strength of contraction is related to the length of the muscle when the contraction occurs. And this length of the muscle, when we're talking about the heart, is how stretched the ventricles are by blood. So increased heart filling stretches the cardiac muscle fibers more at the end of diastole, causing more cross bridges to occur between actin and myosin, which means you have more force of contraction. So contractility is a term used to refer to the heart when it's contractile force. So increased force means increased contractility, leading to more vigorous systolic contraction, which means you're pumping more blood out of the ventricles per heartbeat, and this increases the stroke volume. And as I mentioned in the previous slide, I think the myocardium cannot continue to stretch indefinitely, so when you start to overfill the ventricles, then you'll see the ventricle's ability to pump this blood to start to fall off. This only would occur during heart failure. So we've talked about preload, now let's talk about afterload. So afterload is occurring during systole, and this is the amount of pressure the ventricles must develop to open the semilunar valves and eject blood into the arteries. So remember, the aorta is the artery branching off the left ventricle. The aorta has a fairly high pressure. Diastole, it's diastolic pressure is around 80 millimeters mercury. So the ventricles have to generate more than 80 millimeters mercury to open up the semilunar valves to eject the blood into the arteries. And this pressure is referred to as afterload. The ventricles have to generate a certain amount of pressure that is above 80 millimeters mercury to push open these valves to eject blood. This is afterload. And hopefully you can see how that differs from preload. Preload being how full the ventricles are, afterload being the force needed to open the semilunar valves and eject blood into the artery. So obviously this depends on the resistance to blood flow out of the ventricle, and it's essentially the back pressure exerted by the atrial blood on the semilunar valves. So remember, the diastolic pressure being 80 is the lowest pressure usually in the aorta, so the ventricles have to generate more than 80 millimeters mercury to open the semilunar valves. However, if blood pressure is increased, then this afterload is also going to be increased. So a good example of this is if someone has hypertension. Someone with hypertension has elevated blood pressure, which means the heart has to work a lot harder to push open these valves to eject blood into the arteries. So because the heart has to work a lot harder with someone with hypertension, the left ventricle tends to become hypertrophic, which means it expands, it swells in size. Just like any working muscle, if the muscle has to work harder, it gets bigger in size. Similarly, the heart, if it has to work harder to eject blood due to hypertension, the left ventricle becomes larger in size, and this can have negative consequences on the heart function. So does afterload affect stroke volume? No, not normally under normal conditions. So under normal conditions, afterload does not normally alter stroke volume. But during exercise or during hypertension, you get elevations in afterload because blood pressure goes up, and this significantly reduces the ability of the ventricles to eject blood. So increasing afterload causes a decrease in the amount of blood being ejected, which causes an increase in end systolic volume. Remember, end systolic volume from the last lecture is the amount of blood left in the ventricles after a heartbeat, and this results in a decrease in stroke volume. And you can see here in this figure, under normal conditions, outflow resistance being increased does not alter stroke volume at all. We get a very flat part of the graph up here. But during cases like hypertension, when blood pressure gets up to pathological levels, this is when we start to see a falling off of the stroke volume. So this is in a normal heart. In a heart with myocardial dysfunction, you see big problems where even increasing afterload a little bit starts to cause stroke volume to drop off, which is going to cause problems for the body. Now let's talk about ways we can modulate cardiac output. So remember, cardiac output is referring to the total amount of blood being pumped by the heart per minute. And the equation we use to calculate cardiac output is stroke volume, which is the amount of blood being pumped per heartbeat, times heart rate, which is the amount of beats per minute. So how can we modulate cardiac output? So obviously we want to modulate cardiac output if our body is doing different things. If we're sitting here relaxed, resting, we need a certain amount of blood flow to maintain our body. But if we start exercising, obviously we have to increase the amount of blood going to different tissues to maintain normal tissue function. So if we start exercising, we're going to need to increase cardiac output. So how can this cardiac output be regulated? We can either change stroke volume, or we can change heart rate, or we can change both. And changing one or the other or both will obviously change cardiac output. So let's start off by just looking at things that can modulate heart rate, which are then obviously going to modulate cardiac output. So regulation of heart rate, if we want to talk about that, we first need to define a few important terms. So bradycardia means when heart rate is slower than normal. Tachycardia is when heart rate is faster than normal. You may already be familiar with these terms, they're pretty commonly used in medical TV shows. Chronotropy is a term used when we're talking about the rate of action potential production in the SA node. So remember, the SA node is the pacemaker, which sets the heart rate. Normally, it can work without any external stimuli, but in our bodies, usually we are modulating it using nerves or hormones. Anything that will increase the rate of action potential on the SA node will be described as causing an increase in chronotropy. And it's obviously will cause an increase in heart rate. Dromotropy is something slightly different, and this is the conduction rate of action potentials through the AV node. Anything that increases the conduction rate through the AV node is described as causing increased dromotropy, and this also will increase the heart rate. And finally, inotropy is basically the same thing as contractility or strength of the contraction of the heart muscle. So inotropy is just a term used by biomedical people to refer to the contractility or the force of contraction of the heart. So if you have increased inotropy, this refers to increased contractile strength of the muscle contraction in the heart. And remember, if you're increasing the strength of the ventricular contraction, you're going to increase the stroke volume. Increased strength of contraction will increase the amount of blood being pumped out of the ventricle, which is going to increase the stroke volume. So heart rate can be modulated by direct nervous stimulation, most notably by the autonomous nervous system. or by circulating hormones such as epinephrine. So the autonomic nervous system, ANS, you've probably already had this in previous lectures, is made up of two parts. Both parts are regulated by the medulla and the brainstem, which contain cell bodies for the two main divisions of the autonomic nervous system. You have the sympathetic nervous system and the parasympathetic nervous system. And both the parasympathetic nervous system and the sympathetic nervous system innervate a whole range of different tissues and organs throughout the body. We're just going to be talking about their influence on the heart in this lecture. Just be aware that they do regulate a lot of other things as well. You can see here, parasympathetic nervous system mainly innervates the heart through the vagus nerve, and it decreases heart rate. We'll talk about more how it works on the heart in later lectures. Later slides. Just on the slide here we can see the vagus nerve is the main nerve for the parasympathetic nervous system, coming down from the brainstem, the medulla, and it innervates the SA node and the AV node predominantly, whereas the sympathetic nervous system also coming from the medulla and the brainstem, but this comes down through the spinal cord and then through some ganglions, and also targets SA node, AV node, and the heart muscle itself. So the main activity of the medullary neurons is modulated by input from different sensors and from other regions of the brain. We're going to be talking about one of these specific sensors towards the end of the lecture, the baroreceptors. But there's a whole lot of other different sensors and other brain regions that feed in to the medulla to modulate the activity of the sympathetic and the parasympathetic nervous system, which in turn will then modulate the heart rate. So let's look at the sympathetic pathways first. So the sympathetic nervous system has stimulatory effects on the heart. You can see this is outlined here on the right. You can see different preganglion, postganglion neurons. The main thing you need to take away is the sympathetic nervous system uses norepinephrine as a neurotransmitter, which binds to adrenergic receptors, either beta or alpha receptors, and these are found on the heart, either the SA node, AV node, or the heart muscle itself. And when this system is signaling, and this the postganglion neurons are releasing norepinephrine, and the norepinephrine is binding to adrenergic receptors on the heart, that causes at the SA node to increase heart rate. So it's going to cause increased signaling from the SA node, increasing heart rate. And they call this increase in chronotropy. Increased sympathetic nervous system signaling at the AV node will cause increased conduction velocity through the AV node, and that's obviously called increased dromotropy, which also helps increase heart rate. Increased sympathetic nervous system on the heart will also cause increased contraction strength of the heart muscle itself. This is called increased inotropy. So the force of each heartbeat will be stronger with increased sympathetic nervous system signal. And as I mentioned, the sympathetic nervous system acts via norepinephrine binding to either alpha or beta adrenergic receptors. The beta adrenergic receptors are the main types found on the heart itself. Both alpha and beta receptors are found in the vasculature, so in the blood vessels. Norepinephrine-mediated vasoconstriction occurs via alpha receptors. Epinephrine mediates vasodilation via beta receptors, but at high levels it can activate the alpha receptors, becoming vasoconstricted. Now the parasympathetic nervous system pathways are shown on the right of the same figure. You can see in this case here, the postganglionic neurons release acetylcholine as the effector neurotransmitter. The acetylcholine then binds to muscarinic receptors found on the cardiac and heart cells. This causes the effects on the heart. So the parasympathetic nervous system has inhibitory effects on the heart. So remember, the sympathetic nervous system had stimulatory effects. The parasympathetic nervous system has inhibitory effects. So increased parasympathetic nervous system signaling at the SA node causes a decrease in heart rate, and that's the main effect. And they call this a decrease in chronotropy. Increased parasympathetic nervous system activity signaling at the AV node causes a decrease in conduction velocity through the AV node. They call this a decrease in dromotropy. And this also obviously influences a decrease in the heart rate. And finally, an increased parasympathetic nervous system on the heart causes a decreased contraction strength and a decrease in inotropy. Now this decrease in inotropy is only moderate or mild. It's not the same as sympathetic nervous system's activity on inotropy, which is a dramatic increase in inotropy. But the parasympathetic nervous system does have a small effect on the inotropy. As I mentioned when discussing the figure, the parasympathetic nervous system acts by acetylcholine binding to muscarinic receptors. The muscarinic receptors are also found on blood vessels, including the coronary arteries, and they cause vasodilation. So that's mainly, we've already looked now at the heart affecting cardiac output. Let's look at ways to modulate cardiac output by modulating stroke volume. So stroke volume is determined by end diastolic volume minus end systolic volume. So obviously if we want to modulate cardiac output by changing stroke volume, if we want to change stroke volume, we can change either end diastolic volume or end systolic volume. Remember what each of these are. End diastolic volume is the amount of blood in the ventricle at the start of each heartbeat. And end systolic volume is the amount of blood left in the ventricle at the end of the heartbeat. So stroke volume can be modulated by changing end diastolic volume and or end systolic volume. So end diastolic volume can be influenced by venous return. Remember the Frank-Starling law of the heart. If we increase the amount of venous return, we increase end diastolic volume. This will increase force of contraction of the heart, which will increase stroke volume. So venous return depends on venous pressure, arterial blood pressure, peripheral compliance, local blood flow, and capillary exchange. End diastolic volume is also influenced by filling time. So if we give the heart more time to fill between heartbeats, then we're going to increase the amount of blood in the heart before each heartbeat. So that's increasing end diastolic volume. So if we decrease heart rate, we increase filling time, which will increase end diastolic volume, which will increase stroke volume. Ways which we can influence end systolic volume include cardiac muscle contractility or inotropy. So we increase the force of the heartbeat or the force of contraction, we will then pump more blood out per heartbeat, which decreases the amount of blood being left in the heart at the end of the heartbeat. And this causes an increase in stroke volume. So remember the parasympathetic nervous system and the sympathetic nervous system, which modulate inotropy and modulate contractility, and modulate end systolic volume, thus also modulating stroke volume. And if we can also modulate afterload, we can also modulate the amount of blood being left in the heart, meaning we're pumping more blood out per heartbeat. So we decrease afterload. So if someone has hypertension and we give them antihypertensive drugs, we will then decrease the afterload, which then decreases the amount of blood being left in the heart at the end of the heartbeat. This causes an increase in stroke volume. So let's look at modulating cardiac contractility and afterload a bit more. So modulating cardiac contractility, as I've already mentioned, this can be done by sympathetic nervous system tone. And remember the neurotransmitter regulating the signal is norepinephrine. So if we increase sympathetic nervous system tone, we increase contractility. Circulating epinephrine and other hormones can also influence this contractility of the heart. So epinephrine or adrenaline, if it's released and is floating around in the blood, will make its way to the heart and also increase contractility. Inotropic drugs also exist, which have sort of the same effect as epinephrine, sort of dioxin, it's a positive inotrope, or beta blockers are negative inotropes. They have a negative effect on inotropy, which will cause a decrease in stroke volume. Things that modulate afterload will make it easier for the ventricles to eject blood into the arteries. So as I mentioned, if you decrease arterial pressure, you'll decrease afterload, making it easier to eject blood, which will decrease the amount of blood being left in the heart, increasing stroke volume. And another thing that can influence afterload is if there are stenosis of the semilunar valves. This is a fairly common disease. You can have valve stenosis or aortic valve stenosis, which makes it harder for the ventricles to pump blood into the aorta, which also increases afterload on the heart. So if you repair any valvular defects, you can also possibly fix afterload if there's a problem. Finally, this summary is talking about different things that can all affect cardiac output. So we can see, if we start at the bottom, you can see two main factors influencing cardiac output are stroke volume and heart rate. Heart rate is influenced by sympathetic or parasympathetic nervous system, which is then modulated by exercise or other physiological processes. Stroke volume itself can be modulated by either by end systolic volume or end diastolic volume. End systolic volume is mainly modulated by contractility of the heart muscle, which can be modulated by hormones or the sympathetic nervous system as well. Contractility can be modulated to a smaller part by parasympathetic nervous system as well, but that's more of minor importance. It's mainly the sympathetic nervous system that modulates contractility. An end diastolic volume, or the preload, is mainly modulated by venous return, and venous return can be modulated by heart rate or by exercise. So that's the end of this lecture. If you have any questions with regards to anything I've mentioned in the last two lectures, please feel free to email me. Apart from that, good luck.